Okay guys, welcome to the fourth video. In this video we're going to be talking about how to improve the mechanical properties of ceramics. So in order to do that we need to look back at the defining property for failure in a ceramic we call fracture toughness, called K1C, and last time we saw that it was equal to Y, a dimensionless term that is geometry dependent, times sigma, which is the stress, and we learned in the last video that this stress is the tensile stress that's being exerted on that crack, times the square root of pi. Don't worry about why pi is there, it has to do with the geometry of the sample, times A. And A was our crack length. So sigma, again, is tensile stress that is exerted on the sample. A is crack length. And if we take a look at a sample with a crack in it, A would be this distance. Now it's different for an internal crack. For an internal crack, the total length is 2A. Now, we also have this Y, and I told you that it was geometry dependent. And it depends on two types of geometry in the sample. So the first type of geometry that it depends on has to do with the sample. And what that means is the shape of that sample. So whether or not you have a sample with square sides, or you have a sample that looks, kind of wonky, and how this crack and the loads are associated with the shape of the sample. The second type of geometry that we're worried about is called the crack tip. Now, what this means is that depending on how the tip of the crack is, we will have a different response. Meaning, if the crack is very, very sharp, like that, your Y value will be larger. Sorry, your Y value will be lower, and your fracture toughness will be lower. Whereas, if your crack tip is blunted and round at the end, your Y will be larger. So this geometry dependence is very important. And this crack tip is actually very important if you've ever seen a crack repaired on an airplane wing, or you've seen a crack repaired on a windshield. What they do is they have the crack that ends right here, like that. And what they do is they drill a hole at the crack tip. And so the new crack tip is where this blue color is. And what that does is it blunts the crack and prevents that crack from propagating. So if we take a look at ceramics and their fracture, what we see for a ceramic like chalk, if we look at the stress-strain diagram, what will happen is you'll have one sample that you load and it'll fracture here. You say, okay, this is my fracture strength, this is the yield strength of the chalk. But then you take another sample and load it up and it'll fracture somewhere up here. Well, now you have a different value. So you say, okay, let me take another sample. You load it up and it fractures right here. So you get all this variation in a ceramic like chalk. And this variation will mean that you don't always know how a specific sample will react to a particular load. So if we look at something that we've looked at before, where this is stress or failure stress, and this is population, we'd see that if we have, we see an average failure stress for a particular type of material, and if it were something like chalk, we'd have something very broad like this, where we have a lot of variation in the failure stress of that material. So what ceramic engineers do is they try to decrease this variability. And the way that they decrease this variability is by playing with the types of cracks that are formed in the material. The types of cracks and the shapes, as well as how the cracks propagate. And what that does is it effectively takes this distribution and makes it smaller. And that allows us to use these ceramics in a wider variety of applications. And you will notice that especially in things like knives. 10, 15 years ago, ceramic knives weren't on the market. They were very difficult to find. But now, due to this type of engineering, ceramic knives are quite common, and you can buy them for a fairly low price.